Hi, welcome to AB Video 3.7b Part 2, even more optimization problems. Okay, so I just want to show you some more sample problems. This is a typical problem. An open box of maximum volume, so you're trying to maximize the volume, is to be made from a square piece of material 24 inches on each side. So the actual dimensions on the outside are 24 inches. But what you're going to do is cut these little squares, and they're going to be equal squares from each corner. So if the side length of each square is x, then what's remaining in here, once you cut those away, is 24 minus 2x. Big mistake people make is 24 minus x. So when you toss these little corners away and you fold up these darker blue sides, you'll end up with a box. Of course, the base is square, so it's 24 minus 2x and 24 minus 2x, and the height of the box is, of course, that little x right here. So write the volume as a function of x, and then use calculus to find the critical numbers and find the maximum value, which is the maximum volume. Okay, so we want maximum volume. If we want maximum volume, then we're going to take the volume of a box, or the volume of a rectangular prism, is a length times width times height, which is 24 minus 2x times 24 minus 2x times x, which if you expanded would be 4x cubed plus blah, blah, blah. Now, as far as a domain, obviously x has to be positive, but there is a limit. Since this is, started out as 24 inches long, you're obviously not going to cut out a square of 18 inches by 18 inches, because 18 and 18 is more than 24. So your 24 minus 2x has to be greater than 0, which means in the end your x has to be less than 12. So your actual domain is between 0 and 12. Now, if you were doing it by hand, you'd find the derivative, you'd find the critical numbers, you'd use the number line test. First derivative test on the number line. Of course, it's a number segment here from 0 to 12. You'd find out there's a max when x equals 4. But the question did say find the maximum value. So they actually do want what is the maximum value. So we know what happens when x is 4. We go back to our equation, which is our equation for the volume in terms of x. We replace x by 4. And don't forget the answer will be in cubic inches because it's a volume. Number 26, a rectangle is bounded by the x and y axes, and the graph of y equals 6 minus x all over 2. So here's y equals 6 minus x all over 2. And of course, so it could be, for example, this green rectangle. It's bounded by the x-axis, the y-axis, and its vertex here is on that famous line. It could be this black rectangle. It could be this little tiny, not very high red rectangle. Could be this one, could be that one, could be anything. So I'm just going to pick an arbitrary point x, y on the curve. Keep in mind that the y coordinate is 6 minus x all over 2. So this rectangle that's formed would be a rectangle with length x and height y. They want the area of the rectangle to be a maximum, so we want to maximize the area. The area of that rectangle is x times y, too many variables, which is why I'm going to replace y by 6 minus x over 2. As far as the domain, x would have to be positive because it would have to lie in the first quadrant, and the maximum thing x could be, since this intersects the x-axis at 6, it would have to be less than 6, and et cetera, et cetera, et cetera, et cetera. Okay, so now I'm more interested in just setting up the function and figuring out the domain. You should be able to take it from there. Okay, this is an interesting question. A rectangular page is to contain 36 square inches of print. The margins on each side are 1.5 inches. Find the dimensions of the page. So you're trying to decide, like I don't know, you've written a book and you want to have this book printed. It's obviously not going to be an 8.5 by 11 book. So what should the dimensions of each page be is what we're looking, so that we can, what we're looking for. And the question is to use the least amount of paper. So we know the printed area right here is supposed to be 36 square inches. The margins are 1.5 inches on each side. So if we look at the piece of paper itself, which is the blue, obviously, if I call this x and this y, which is the length and width of the printed area, then this is going to be x plus 3 because I have the x, and don't forget I'm adding 1.5 on both sides. If this is y, then this is y plus 3 because, again, I'm adding the 1.5 top and bottom. So we want to make use the least amount of paper, which is the minimum area of that blue piece of paper. The area of that blue piece of paper is x plus 3 times y plus 3. Again, too many variables, which is why they told you there's 36 square inches of uh, print. So x times y is 36. Y is therefore 36 over x. Come back, replace y by 36 over x, etc. The domain here is that x would have to be greater than 0, obviously, and then you just find the derivative, the critical numbers, etc. And keep in mind, for one question on the next test, I will ask you for the actual AP justification, which is kind of reading the number line to me. This question is not in the book, and they actually will never ask this question because no matter if you just have a rectangle and you're not splitting it up into any other figures, and so you have, let's say, 200 feet of fencing to make this rectangle, um, the, in order to get the maximum area, the answer will be that it has to be a square. So they'll never ask this question because they know you'll know that. But just so we can walk through it, so the amount of fencing, which is x plus y is 200, which makes x plus y equal to 100. We want to maximize the area, so the area is x times y. Too many variables. Come over here, isolate y, plug it in. There's your equation. Your x obviously has to be positive. Now it has to be less than 100, and the reason it has to be less than 100, if for y to be positive, then x can't be bigger than 100 because then y would be negative. So you have a number A, here's your first derivative, critical number, etc., etc. Don't forget to answer the question with units of measure. This is like number 40. A tank is formed by adjoining two hemispheres, which is half spheres, to the ends of a right circular cylinder. The volume of the tank must be 3,000 cubic feet. That's the whole tank. The hemispherical ends cost twice as much per square foot of surface area as the sides of the tank. God forbid they tell us how much, just twice as much as this mysterious unknown amount. Find the dimensions that will minimize cost. So we want a minimum cost. So our equation, our function is going to start with C equals. Now, obviously, the cost is going to be the cost to produce the ends plus the cost for the sides, which is around the cylinder. Now, we don't know how much the cost per square foot is for each one. All we know is that the ends cost twice as much. So the cost of the ends will be the cost per square foot of the ends, the hemispherical ends, times the area of the ends. And the cost of manufacturing the sides of the cylinder will be the cost per square foot of that material times the area of the sides combined. Okay, so if we call K this unknown constant, which is the cost per square foot of the sides, since the ends cost twice as much, their cost will be 2K. Keep in mind K is a constant. Now, the areas of the ends, well, that would be the outside area of that hemisphere plus the outside area of that hemisphere, which actually is just the area of the whole sphere, which is 4 pi r squared, surface area of a sphere. And then the sides, of course, is the lateral area, so think of wrapping it in string. Each string will be the perimeter, which is 2 pi r times, which is the circumference of the circle, times h, so 2 pi r h. So here's your cost formula. Unfortunately, too many variables, C, R, and H. So we need to isolate one of those. Now keep in mind K is a constant. Well, the reason they told us that the tank has to have a volume of 3,000 square feet is because that'll give us a relationship between R and H, and I'll be able to replace that. So the volume of the whole thing is the volume of the cylinder plus the volume of the sphere. That has to equal to 3,000. Volume of the cylinder, pi r squared h, plus volume of the sphere, 4/3 pi r cubed. Which then if I isolate, now when you're deciding which one to isolate, way easier to isolate h because there's r's in both terms. H is only in one term. So I isolate the term with the h, then I isolate the h, and then I simplify. And after all is said and done, h is equal to 3,000 over pi r squared minus 4/3 r. So I come back up to my equation that had too many variables. I replace h by the quantity I just found. blah, 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 simplify, find the derivative, domain, the radius would have to be positive, critical numbers, first derivative test, and you find out, sure enough, there's a min at the cubed root of 1125 over 2 pi. Feel free to use your calculator to approximate that to 5.636. So what happens when r, which is our variable, is that many feet, and then of course h, you'll plug it back in the r in here to find